Dear students, in physics, in the section heat, now we are going to see another interesting experiment. See what it is. Determination of the specific heat capacity of a liquid by method of cooling. We are going to use the cooling method of cooling to find the specific heat capacity of an unknown liquid. First, try to understand the concept. What we are going to do here, considering two warm bodies cooling in a continuous stream of air, if the nature and areas of their surfaces and the excess temperature of the bodies over that of the surroundings are all identical, then their mean rates of loss of heat will be equal. I will explain. Listen, what that means is, say you have a calorimeter filled with hot water. Let's say hot water is at 80 degrees centigrade at a particular moment. If hot water is 80, if I keep a stir and stir it continuously, I can assume this surface also will be at 80 degrees because it's a thin metallic container, right? So heat will get transferred quickly. So outer surface is going to be at 80 degrees centigrade. Whereas let's say the surrounding is at 30 degree. Surrounding is at 30 degree, room temperature. What will happen from the substance with high temperature to the surroundings? Heat will be lost. So I can show the heat transfer from this surface. Let me mark from the surface. From this surface, heat is going to be lost. This heat loss rate, there is a formula for that. The heat loss rate is equal to K A theta 2 minus theta 1. Let me explain what these are. K is a constant that depends on the nature of the substance. This substance. That means, if the surface is made out of copper and if the surface is made out of aluminium, the rate at which they emit heat or they release heat will be different because the surface type is different. Understand, the type of surface is different. So this K is a constant that reflects the type of surface. K. A is the area. How much area, right? If we increase the area more and more, it loses heat faster and faster. The rate at which heat is going to be lost to the environment will increase if the area in touch with the environment, area in contact with the environment, if it is increasing, heat loss rate also will increase. Theta 2 minus theta 1 means excess temperature. Excess temperature means, now in my example, this is theta 1, this is theta 2. Surface is at 80 degree, surrounding is at 30 degree, theta 2 minus theta 1. The excess temperature in this case 50 degree, right? If the excess rate is high, the heat will flow faster. See, I'll tell you another example. When the water flows, right, from a very high point, if the water is falling, it comes very fast, right? The height is high. But if the water is falling from a smaller height, still the water will flow, but the flow rate will be less, right? It flows slowly. If the levels are equal, it doesn't flow. If the levels are equal, if the flow levels are equal, water doesn't have to flow, right? Same story here. Compared to the surrounding temperature, this surface has very high temperature, then the temperature flow, the heat flow will be faster. So excess temperature is that. These are the three factors that decide from a surface, from a hot surface, how the heat is going to be transferred to the environment. The nature of the substance or nature of that surface, that basically depends on what material it is. Whether it is copper, aluminium, plastic or something else, it will decide. If there are some materials that won't release the heat easily, they will hold on to it. Some materials very easily they release it. So that's that K. A is the area. Higher the area, more heat loss it will be. Third one, excess temperature. So what's key here? Did you see this formula doesn't tell anything about what is inside here? Whether we have hot water, whether we have hot oil, or whether we had some other substance here, doesn't make any difference, because it's K surface type, A surface area, theta 2 minus theta 1 the surroundings, and the surface excess temperature. So what material we are using inside here, whether we keep oil here or water here, doesn't make any difference. So that means look at this. If I take two identical calorimeters, why I say identical calorimeter is K has to be same. If this is copper calorimeter, that also has to be copper calorimeter. Then only K will be same, identical. Surface must be equally polished, identical calorimeters, so that K is same. And fill one with water. Another one with some other material, let's say some oil, unknown specific heat capacity it has. But if we have filled it same amount of water and oil, then the area from which heat is going to be lost will be same for both, right? So K is same, A is same, right? Surrounding for both is going to be 30 degree. If surrounding is 30, let's assume it's 30. Then when this is at 80 degree, if this is also at 80 degree, the rate at which they are going to lose heat to the environment, it's same, because K is same, because identical calorimeters, area is same, theta 2 minus theta 1 is same, excess temperature 30, 80, 50, 30, 80, 50. Both are going to have same rate at which heat will be lost to the environment. One is water, one is oil. Do you understand? What material we use inside the calorimeter doesn't matter, because calorimeter surface is where all depends on. K type of surface, A surface area, theta 2 minus theta 1 the temperature difference. So whether it is oil or water or what it is doesn't matter, right? That's what the sentence says. Considering two warm bodies cooling in a continuous stream of air. Why we say continuous stream of air? From here, when the heat comes out to the surroundings, the air molecules around that calorimeter will absorb that heat. So sometimes those air molecules, the ones which are close to the calorimeter, their temperature might go up a little bit. To avoid that, what we do, we give continuous airflow. That means whichever the molecules or whichever the air particles will not remain there for a longer time. They get the heat and they keep moving. Get the heat and keep moving. New air comes. So that 30 degree will be maintained. In the old books, they say you can keep this arrangement near a window and do it, because near a window the airflow will be more or less constant. But nowadays we have electric fans. You can keep a table fan, and in front of table fan, if you do this arrangement, airflow will be constant, right? So considering two warm bodies cooling in a continuous stream of air. Why do they say continuous stream of air? Listen, from this calorimeter, when the heat is being released, the air molecules around that are going to get that heat, right? And sometimes their temperature might increase from 30 degree. So to avoid that, that means to maintain the surroundings at 30 degree itself, what we do, you give a continuous flow of air. So no air molecules stay around this calorimeter for a longer time. Whichever the ones getting the heat will keep moving, because there is continuous flow of air. In the old books, they say you can keep this arrangement near a window and do this, so that near the window you can assume the flow is uniform. If not, nowadays we have electric fans. You can keep a table fan and do this. so that the flow, uniform flow of air will be there. If the nature and areas of their surfaces and the excess temperatures of the bodies over that of the surroundings are all identical. See, if all are identical, excess temperature is identical, surface area is identical, surface type is identical. If all these three factors are identical, then their mean rates of loss of heat, that's what we call Q by T. Rate of loss of heat will be equal for both. Right? At the same time, you know how there is another way to write Q by T. What is the other way to write heat loss rate? Look here. You know, heat loss rate can be calculated as m c delta theta by delta t. That means for example, let's say a container of water which has 100 grams of water from 80 degree, if it has come down to 60 degree, it's water, so 4200 joule per kilogram per Kelvin, then the heat loss rate will be m, convert that to kilograms, c delta theta 20. Let's say it took let's say 2 minutes for this, 2 minutes, then you will put 2 into 60. Solve this, 3 zeros, 2 0, 1 0, another 0, 2, 6, 42, 7, 70 joules per second. It loses heat at 70 joules per second. Right, what did we do? Because mc theta is the heat content. So if the heat reduces, m doesn't reduce, c doesn't reduce, only the theta reduces, right? So keep m and c constants, find the rate at which theta reduces, that is what the heat loss rate as well. So heat loss rate can be written as mc d theta by dt or delta theta by delta t. That means the rate at which the temperature drops, the cooling rate. We already said dq by dt for water is going to be same for oil. Under the above mentioned conditions, I gave you some conditions. Same calorimeter, same amount of water and oil, you are considering the same temperature of both of them, then this will be same. Now according to this one, you can say mc delta theta by delta t, the time taken for that. For water you apply this mc delta theta by delta t. For oil also you apply this. What the mass of both we can measure. We can measure the mass. Water's specific heat capacity we know, but when you are writing this, we have to consider there is a calorimeter as well. So we'll write like this, including the calorimeter. Calorimeter is also going to lose heat, right? Because the temperature of calorimeter and water are same. So we'll write this. Here when you say water, that includes calorimeter also. MCCC, NWCW, both of them are losing heat. Delta theta by delta t. For this you can write, again calorimeter is there. This time it is oil into delta theta by delta t. You apply this formula. You can measure the mass of calorimeter, oil, water, everything you can measure. Water specific heat capacity, usually we take it as 4200, theoretical value we know. Calorimeter specific heat capacity is 400, we know that it's copper. Delta T, delta theta we can get from the experimental procedures. When you do the experiment, you can find out from what temperature to what temperature it has gone down. We can find it. Delta theta, delta T, you're going to start a stopwatch and find the time as well. Apply all these values. What is missing is C naught, CO, specific heat capacity of oil. We are going to find that. Clear? So this is the experiment. See, this is the concept behind the experiment. What is it? You let water cool on its own, cool in its own. Under the same conditions, in the same container, same amount of oil from same temperature to same temperature. Let oil also cool. We'll draw a graph. The cooling curve will be drawn. From the cooling curve, at some particular point, we will find the heat loss rate, the rate of heat loss. We will equate that for both. From that, we can find out the specific heat capacity of oil. Clear? Are you clear with the concept? Right. Now, this is what I was telling about. The graphs. You draw the cooling graph. See, with time, how the temperature changes. Water's temperature drops like this. Coconut oil's temperature drops like this. You compare particular two temperatures, let's say from 80 degree to 60 degree. How it drops? Just compare two different temperatures. So look at the green graph, which is for coconut oil. See, from this point to this point is what you are considering. It has taken T1. For water, it has taken time TW. Can you see? So I can write for water MCCC MWCW. Delta theta means it drops from theta 1 to theta 2. And the time it has taken for water, TW. This is the heat loss rate, average heat loss rate within this gap. Average heat loss rate within this gap. Similarly, when we do this for oil, again MCCC, because calorimeter is always there, M oil, C oil, theta 1 minus theta 2 over T liquid. Now you can say if you maintain the same conditions, same calorimeter, same amount of oil, if you maintain all of that same, then the heat loss rates have to be equal. Equate these two, theta 1, theta 2, TW, TL you are getting from this graph. MW, MC we can measure from the experiment. Only thing that you don't know will be CO. CO that we can find. Clear? See again. Water, this is the heat loss rate. Coconut oil, this is the heat loss rate. You equate both of them. We can find CL. Right, this is what the concept is. Now see how the experimental procedures are going to be. Materials and apparatus. A calorimeter having a polished outer surface and containing a lid and a stirrer. A thermometer, an electric fan. I told you the reason why we need an electric fan. We are going to maintain constant airflow. A stopwatch, a triple beam balance, sufficient quantity of water and the liquid. See, one more thing. In the exam, if you just write balance, you don't get marks. You have to say triple beam balance, or you can say chemical balance, or you can say electronic balance, right? If you simply say balance or weighing scale, you don't get marks, because in the lab when we use for experiments, we have to use these particular types of balances or weighing scales only. You can't use all the scales for that. Yes. Method. Measure the mass of calorimeter with stirrer MC. Fill up to about 1 centimeter from the top of the calorimeter with water heated to 80 degrees centigrade. Close with the lid and suspend from the stand. Now wait. I made a statement here. If this is your calorimeter, from the top 1 centimeter below, you fill it with water, hot water. So what is this 1 centimeter story? Why can't we fill it just to half of the calorimeter and do this experiment? Problem, if you fill it to half of it or to a lower level, imagine if this is 80 degree, this part of calorimeter surface will be 80 degree. But you can't ensure this part to be 80 degree, right? You understand? Because water is only up to here. So it will not be 80 degree. Above that, the surface will not be 80 degree. So the cooling rate is not going to be equal, right? Cooling rate at this point is different. Cooling rate at this point is different because it has a different temperature. So heat loss is going to be affected because of that, right? So by filling the hot water or hot liquid to as much as possible, but you don't fill it up to the top because it will be spilling out and all that. It's very difficult to do the experiment. You have to take the measurements. So, and you have to keep stirring it. So, keeping space for that, that's why we say 1 centimeter below the top, you keep stirring it. By doing that, you can ensure this surface, right, the entire surface of calorimeter is at the same temperature as of water. So, there are two precautions measures we are taking. One is filling to this level. Second thing is stirring it continuously. Until from the start of the experiment until the end of the experiment, you have to keep stirring it. Otherwise, the water might not have even temperature throughout. Some part of water might be hot, some part of water might not be that hot. And also the water and the calorimeter's walls will not be at the same temperature. To ensure all this, we keep stirring it continuously. Let the calorimeter cool by the continuous flow of air from the electric fan placed near the calorimeter. While stirring the water continuously, observe and note down its temperature at 30-second intervals till the temperature falls to about 40 degrees centigrade. Right? Every 30 seconds we are going to measure the temperature. So, you already have kept a thermometer inside. Keep stirring it every 30 seconds. That's why you have to switch on the stopwatch. Right? In the stopwatch, every 30 seconds, you check the temperature in the thermometer and write it down. From 80 degrees centigrade to 40 degrees. You will have a number of readings after that. Then we can draw the graph. Y-axis, I have shown you a graph here. See this graph. Y-axis temperature, x-axis time. We will be able to draw this graph. If we draw this graph only, we can take 2 points and we can do these calculations. Clear? So, come back and see here. While stirring the water continuously, observe and note down the temperature at every 30 seconds. This is for water you are doing it. I need 2 graphs, one for water and one for the other liquid, right? Next, measure the mass of calorimeter with water. Already you have measured the mass of calorimeter and stir only. Now with water you measure it. So if you get the difference, that has to be the mass of water. Now remove the water from the calorimeter, wipe it well, fill it with an equal volume of heated liquid and repeat the experiment in the same manner. So what you did for water, now you have to repeat for the oil or whatever the liquid. That also you get the temperature readings every 30 seconds and note it down. After recording the readings, measure the mass of the calorimeter with the liquid, because we need the mass of liquid as well, right? So now with the calorimeter, measure the mass of liquid also. Already we have the empty calorimeter's mass, the difference will be the liquid's mass. Clear? This is all the experimental procedures are. Now let's start doing the experiment. While doing it, I will explain further about each step we are doing it. Already I have explained here. That should give you a clear understanding of the experiment. Shall we see how to do it now? The material and apparatus required for this practical experiment include the liquid of which the specific heat capacity that we are going to find. In this case, this is coconut oil. We are going to find the specific heat capacity of coconut oil. We need a calorimeter. It is the same calorimeter that we have used to draw the cooling curve of water, because you need the same calorimeter and you have to use the same amount of liquid. Then only we can assume the heat loss rate is equal for both, because the surface area has to be same, right? So we use the same calorimeter with the lid, and the surface of calorimeter has to be polished so that the radiation can be avoided. We need a stirrer. Same stirrer we used earlier for drawing the cooling curve of water, same stirrer. we have to keep stirring the liquid so that the temperature is maintained same throughout the liquid. Then only the temperature we measure is the same temperature everywhere within the liquid. We are using a fan here. Why do we need the fan? To maintain the constant airflow. Either you can use the fan and maintain constant airflow. If not, you can do a setup such that the environmental conditions do not change. At the end of this experiment, I will show you, if you don't have a fan, if you can't maintain constant airflow, how you are going to maintain constant environmental conditions. We need the stopwatch. Every 30 seconds we measure the temperature, because you are going to draw the cooling curve, which is temperature against time. X-axis is going to be time. We need to measure time. Thermometer, every 30 seconds we have to measure the temperature. We need the thermometer. And this is the stand. We hang this calorimeter using a string on this stand. And this time we need a 3-beam balance as well, because what we are going to, the calculation we are going to do this time, mc delta theta by delta t for water and this liquid will be equal. mc delta theta by delta t will be equal, because we are using the same surface area for both. The heat loss rate have to be equal. So we need m, mass, we have to measure the mass. How do we measure that? We need this 3-beam balance. This is all the apparatus we are going to use. First, before we start heating up the oil, first we will measure the weight of this calorimeter with the stirrer. Then we will measure the weight of calorimeter, stirrer and the water, so that we can deduct and find how much of water we have used. After that, we will start the experiment with oil. We will finish it, we will start it at approximately 80 degree and we will come down up to 40 degree. We will finish it. Then we will measure the weight of oil plus calorimeter as well. From that, if you subtract the weight of calorimeter, you can find the weight or mass of oil that we have used. So as I mentioned, now let's measure the weight of calorimeter and the stirrer. Let's keep the calorimeter and the stirrer together and check the weight. It's less than 100. It's in between 0 and 100. Keep it at 0. More than 30, 40, 50, 60. It's more than 70 as well. It's less than 80. So it has to be in between 70 and 80. Let's keep it at 70. 75. It is more than 76, it's close to 77 now. We have to make sure the 0 and this line are aligned at the same line. Yes. Now the weight we are getting here is 77 grams. 77 grams. Right? That is the calorimeter and the stirrer. Let's write down all these values on a table so that at the end we can use these values to do the calculation. Let's write them down now. The mass of calorimeter and the stirrer, 77 grams. Let's write it down. So what is next? We have to get the weight of calorimeter, stirrer and the water. How much of water did we use? The water level was just 1 centimeter below the top level or the brim of the calorimeter. So we will fill water with that much and again measure the weight of calorimeter, stirrer and water together. The calorimeter, stirrer and the water together. Let's bring these to 0. more than 100, more than 200, more than 300, more than 400, but less than 500. So let's keep it at 400. Right. It's less than 410, so it has to be in between 400 and 410. Let's increase one by one. 404, 5, 6, 8, 'We have to wait until it stops. Yes, now it is at 0. The measurement we are getting here 408.8 grams. 408.8 grams. This is calorimeter, the stirrer and water together 408.8 grams. Let's write it down. MC plus MW is 408.8 grams. 408.8 grams. Right. So this is from the previous cooling curve. What we have used, I have got the weight. Now what we are going to do, we have to heat up the oil, right? Since it is coconut oil, we can take it up to 80 degree. You have to be careful, some liquids might be flammable at very high temperature, then you should not go up to 80, right? You may have to start from 60, 70 like that. Since I know coconut oil we can heat up to 80 degree, let's start at 80 degree and let it cool down until 40 degree. And let's do the same thing that we did for water, write down the temperature every 30 seconds and draw the graph. Students, now you can see the oil that has been heated. Let's fill the heated oil to the calorimeter to the same level to which the water was filled earlier, right? Then only we can ensure the surface area for water when it was cooling and the surface area of oil when it is cooling is equal. To ensure that, let's fill this hot oil into this calorimeter to the same amount of water we had earlier. Right. You can see it has come to the same level, just 1 centimeter below the top level, the brim of this calorimeter. Let's close this with the stirrer. And let's keep the thermometer as well. Right. Let's keep mixing it and see what the temperature is. As you can see now, it is above 80 degrees. It is not at 80, it is more than 80. So we will wait for a couple of minutes until it reaches 80 because it has to cool down. And when it reaches 80, we will start the stopwatch and start writing the temperature every 30 seconds. Let's wait until it comes down to 80. Until then, what we can do, we can switch on the fan we can ensure the constant flow of air. Right, make sure the flow falls onto the colorimeter, keep mixing it. When it becomes 80 degree, let's start the stopwatch. Still it is above 80. Right students, as you can see now, the temperature is 80. Let me switch on the stopwatch. Let me write the first temperature, 80 degree. In the same way we did for water, you have to keep stirring it. Make sure the fan is working, constant airflow is maintained. Every 30 seconds, let's write down the temperature. Make sure you are keep on stirring it. (74 degrees), 74 degrees. Keep stirring it. Maintain the constant airflow. Keep stirring it so that the temperature is uniform within the liquid. And every 30 seconds, let's write down the temperature. (68 degrees), 68. We are using the same amount of oil as of water in the same colorimeter so that the surface is same in area. But the cooling rate will be different. (63 degrees), 63 degrees, 63 degrees. The heat loss will be same, heat loss rate will be same, but the cooling rate will be different because M and C are different. The mass of water, mass of oil is different, specific heat capacity is different. Because of that, delta theta over delta T will be different. (58 degrees), 58 degrees. Maintain uniform temperature within the oil or within the liquid. That's why we keep on stirring it. Every 30 seconds, at equal interval, we are measuring the temperature. 54 degrees, 54. 54 degrees. Make sure the fan works in the same speed. The speed doesn't change so that constant airflow is maintained. (50 degrees), 50. 50. We have to do it until it becomes 40 degrees. Until 40, let's do this. You can see initially it started dropping at 6 degrees for every time gap. Now it has dropped only 4 degrees. 4 degrees. 47 degree. 47 degree. The next 30 seconds will finish at 4 minutes. (44 degrees). 44 degrees. Let's continue until 40 degree. You remember the room temperature was 28.5. So when the temperature becomes closer to the room temperature, cooling rate will be less. (42 degrees). 42 degrees. It's 40 degree now, 40, right? So that many readings will be enough for us. We started at 80 degree and we have got the readings up to 40 degree. Every 30 seconds we were getting the readings. Now you know the following steps. Already we have drawn the cooling curve for water, theta against T. On the same graph sheet, on the same axis, we are going to draw the graph for this liquid as well. Then we can select two particular temperature and find the time taken to drop from one to the other. Find it for oil separately, water separately, and then you can say MC delta theta by delta T should be equal for water as well as oil. Why? The surface area is what that decides the heat loss rate or heat transfer rate. We maintain the surface area equal for water and oil. Since the surface area was equal and we use the same calorimeter, there was no change in the calorimeter, we can say the heat loss rate should have been equal. That is why I say MC delta theta by delta T will be equal. We already have found the M of water. Now let's measure this calorimeter, stirrer and oil. Let's get the weight of that. Then we can subtract the weight of calorimeter and stirrer so that we can find the mass of oil we have used. With that we should be able to do the calculations. So shall we measure this weight and see how much it is now? So now the weight of calorimeter, oil and the stirrer. Let's bring all these to 0 and see which 100 it is in. It seems to be less than 400. Bring it to 300 and see. It's more than 300. So let's keep it at 300. 340, more than that. 380, more than that. It's less than 390. So let's keep it at 380. Increase one by one. 383. 384. It's 384.1 grams is what we are getting. 384.1 gram. That's the mass of oil, the stirrer and calorimeter we have used. Let's write this down also in our table now. So MC plus MO, calorimeter plus stirrer and oil together, the weight is 384.1 grams. Let's write it here. (384.1 grams). From this we can find, if I deduct these two, if I get the difference between these two, that will be the weight of water that we have used, the mass of water we have used. Similarly, MC plus MO difference will give me the mass of oil I have used. M can be found. We know C, the specific heat capacity of water is 4200, right? So that can be used. Delta theta by delta T we can get from the cooling curve. Only what is going to miss here, the specific heat capacity of the oil or the liquid that we have used. By equating MC delta theta by delta T, the heat loss rate for oil and water, if we equate with the figures we have got, we should be able to find the C, specific heat capacity of oil that we have used here. Let's calculate and see that now. Students, I mentioned earlier, when we did the experiment, I used a fan and I maintained constant airflow. But there is another option to do this experiment. What is that? Maintaining constant conditions in the surroundings, unchanged conditions in the surroundings. If you can't get constant airflow, that is the other option you have. Let me show how we are going to maintain constant surrounding now, right? This is the other option to do this experiment, right? You can do this setup as well to do the same experiment. We will take a beaker. Then, can you see I have 3 thermal insulators. I am using cork, 3 corks here. They are thermal insulators. Keep those 3 at the bottom here. Right. Then what we do, take another calorimeter where I have already kept weights there. Keep that calorimeter on top of those 3 insulators. Keep it like that. Now you can see there is a gap between this beaker and this calorimeter. The gap between these two we are going to fill with cool water. Right? So I have cool water in this beaker. Let's fill this with cool water. I will show you what will happen after we fill this with cool water. First we will fill this with cool water to the height of calorimeter. Since I have kept weight inside the calorimeter, it does not float. Right. Now you can see this beaker and there is water, a layer of water. Inside that we have the calorimeter. Now this is the calorimeter where we are going to have water or oil. We are going to measure the temperature. It will be at 80 degree and then we let it cool until 40 degree, measure the temperature, all that will be in this calorimeter. How we will do the arrangement, look at this. We will hang this calorimeter using a string inside make sure it does not touch the other calorimeter, the calorimeters do not touch each other. Just hang it in the middle. So this is where we are going to have the hot water or the hot oil or whatever the liquid for which we want to draw the cooling graph, put it here. Now what will happen, from this calorimeter and oil or hot water, the heat will be released. That heat will be absorbed by this cool water. So that the environment, the surrounding between this inside calorimeter and the other calorimeter, that will remain the same. The temperature of that will not increase, it will remain the same, because since I have used cool water here, it will absorb all the heat. Ideally, we have to use water only here. You should not use any other liquid here because it has to have high specific heat capacity so that it can absorb all the heat rapidly. If you use any other liquid like oil which has low heat capacity, it will not be able to absorb all the heat faster. Then the surrounding temperature might increase. That's why we use cool water here. 2 reasons. Cool water, the temperature will be less. Since it is water, it will have high specific heat capacity also. So the temperature, the heat released by this internal calorimeter will be gained or will be absorbed by this water faster. We can draw the cooling curve of water. When we change it to oil, make sure you change this outside water again to the same cooling water that you have used earlier. Why? Then only we can ensure the surrounding was same for water as well as oil. Right, if you use the same water, imagine when the hot water was releasing its heat, this water outside would have gained that heat. So temperature of this water would have gone up. Without changing the water, if you do the experiment for oil, sometimes this internal temperature, the temperature between the two calorimeters might be different. So when you restart it for oil, make sure this outside water is again replaced with cool water. This is the setup we use to do this experiment. If you can't get constant airflow, this is the setup we use to maintain constant surroundings. Right? You can draw the cooling curve with this kind of setup also. Right? So be familiar with both. Sometimes in the exams they ask about both. They ask why do we maintain this setup. Be familiar and understand why we are doing this. So this is all about this experiment. I have shown you both methods of doing this experiment. Go through this once again, right? Understand each step, why we are doing it, how we are doing it. As I always say, the experiments in heat might look simple. The steps might look simple. But the logic behind each step, why we are doing this each step, the understanding about the reason for each measure we are taking here is important. So hope you understood all these steps and reasons for each measure we have taken. Practice this very well. Go through this again, and we'll meet up again with another experiment in physics. Students, you can see here the readings that we have got in this experiment. MC77, that's the mass of calorimeter. Calorimeter and water, it's 408.8. Calorimeter and the oil that we have used is 384. You can calculate MW. The difference between these two will be MW, right? That is 408.77. So that's 331.8 grams. M oil will be the difference between these two. 384.77. 307.1 gram. Room temperature is given. This is for the oil, coconut oil we had, right? This is for water. Every 30 seconds what we recorded, what we have here. Now what we are going to do, we are going to draw the cooling curve for water and oil on the same graph sheet. Let's take a graph sheet. Let me mark the axis now. This is where we are going to take time in minutes. Let's take the y-axis. That's where we are going to take the temperature. In degrees centigrade. Let's mark the scale. Check the time. Water is the one which has taken longer time. 3, 6, 24 readings are there, which is approximately 12 minutes. 12 minutes. 12. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 32 are there. 32. Maybe we can extend that a little bit further to 36. Then what we will do, we will take every 3 blocks, we will take it as 1 minute. 3. So you can see here, I'll show you clearly. Let me take this as 0. After 3 it will be 1. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And then the y-axis, you know, the maximum temperature we have is 80, the lowest is 40. We don't necessarily have to start from 0, we can start from 40 itself. 40 to 80. 40 to 80 is what we need. 40 to 80. Let me show it to you clearly. So if I start 40 here, 2, 4, 6, 8, 10, 12, 14, 16, 18, up to here it's 20. Let's extend that a little more. Right. 40. We'll take 50 here. 2, 4, 50. 60. 70. 80. That's enough for us. 80. That's enough. Now let's mark all the points. First one, let me draw the graph for oil. 80, 74, 68. First point is 80. Let's use a different color to mark the points. First one is 80. T0 is 80. After 30 seconds, it's 74, isn't it? 74 and then 68. 74. After 30 seconds, it's 74. This is 70, 75. 74 is here. Then 68. 67.5 is this. 68 must be here. 68. 63, 58. 63, 62.5. 63 and 58, 54. After 2 minutes, it's 58. 57.5 is this. 58 has to be there. Then 54, 54, 52.5, 55, 54 must be here. 54. 50, 47, 50. 50. 47, this is 47.5, so a little lower than that. 47, 44, 42, 40. Carefully you have to mark the points. 44, 45 is here. 44 has to be a little lower than that. 44, 42. This is 42.5. And then 40. That's how the graph is for, the points are for oil. Oil. Let me draw the graph. Let me draw the graph. Right. That's how the cooling curve is for oil. Can you see it's a nice curve you get? Initially it drops faster, and with time, right, when the temperature drops, the rate at which it falls decreases. Initially it's steep and then the steepness decreases. You can see that. This is for oil. Let me name it oil. Let's name it here oil. The next one I have to draw the graph for water. Water. Mark the points. That also has to start from 80, same point. Then 77, 74, 71. 77, 75, 77. 74. This is 75, 74. 71. This is 72.5, 71. 71. Then 68, 65.5. 68, 67.5, 68. 68. 65.5, 63. 65.5. Oh wait, 68 we have not marked it correctly. See, 68 must be, this is 70, this is 67.5, 68 must be here. 68. Then we have 65.5, 65.5. This is 65, a little bit above that, 65.5. 63, 62.5 is this, a little above that, 63. 60.5, 60.5. 60.5. This is 60. 60.5. 58, 56. 58, 57.5, 58. 56, 55 is this, 56. 56. Are we right marking 56? No. 4.5 minutes. Must be here. That's 56. Carefully mark the points. Then 54, 52, 50. 54. 52.5. 54. 52. 50. That's 50. 48.5, 47. 48.5. So this is 47.5, 48.5. 48.5. Then 47, 45.5. 47. This is 47.5, isn't it? 47. 45.5. This is 45. 45.5. 44.5, 43.5. 44.5. This is 42.5. 45, 44.5. After 44.5, what do we have? 43.5, 42.5. $43.5. Look at this line. This is 42.5. So 43.5 must be above that. Then 42.5. After 42.5, it's 42, 41.5. 42. 41.5. 41.5. 41, 40.5, 40. 41. 40. That's how the graph of water you are getting. A nice cooling curve. You can see the shape is coming properly, except from 1 or 2 points which are a little bit away from the normal curve. Simple. That's how the cooling curve looks like for water. Can you see? Connecting all the points, couple of points just deviated a little bit, right? This is how. You must draw a freehand curve. You can't keep the ruler and draw it. It has to be a freehand curve like this. This is how the curve for water is obtained. We all know water must take more time, because even though mc delta theta by T is same for both the oil and water, water has high C, specific heat capacity is big for it. Since specific heat capacity is big, delta theta by delta T has to be small. That means the cooling rate will be less. It doesn't cool faster because of high specific heat capacity. Clear? Right. Now what do we need? Let's mark two temperature points, two temperatures on this graph. Let's mark two temperatures on this graph. Let's mark two temperatures. Let's say we'll take some known points. 50 could be 1 point, and maybe 60. And 60 are the temperatures I am considering. Cooling from 60 to 50. I need to find the timings. Right. Let's mark the timing. Look at this. This timing is going to be the timing for the cooling of oil from 60 degree to 50 degree. 2 to 3, it's 1 minute. How about this gap? That's like 2/3 of this one block. Altogether 3 blocks is 1 minute, right? 3 blocks are 1 minute. 3 blocks are 1 minute. That means 3 blocks are 60 seconds. I'm going to divide that by 9 blocks, because 3, 3, 3 and 2. You understand? This is like 2/3 of a block. Altogether there are 9 blocks. So 2/3 of 2/3 of one block. There are 3 blocks like that. So it's like 2 by 9 of 1 minute, which is, I can say, which is 1.22 minutes. Similarly, the time here, 6:54. There are 2 minutes here. This is like half of it, right? So that's like 2.5 minutes. 2.5 minutes. 2.5 minutes. See that clear? From 60 to 50, oil has taken 1.22 minutes, whereas water has taken 2.5 minutes. Now let's do the calculations. What calculations? Look at this. We already have written MC, CC, MW, CW, delta theta by delta T equals MC, CC, M liquid, C liquid into delta theta by delta T. MC 77 grams. So that will be 77 by 1000. CC 400. MW water 331.8. 331.8 thousand into CW is 4200. Delta theta by delta T 65 to 55. No, 60 to 50 is 10. The time taken for water's cooling, it has taken 2.5 minutes. 2.5 minutes equals, for the other one, MCCC, same 77, 400, ML 307.1, ML or MO, whatever, 307.1, CL we don't know, 10 over 1.22 seconds it has taken. 1.22 seconds it has taken. Now, you have 10 both sides, you can cancel it. We should have written 1000 here. It's like this. Either write everything in grams, then you don't have to convert it to kilogram. If one is converted to kilogram, everything has to be converted to kilograms. But finally, these thousands can be cancelled. 1000, 1000, 1000. 77 into 400 is 30,800. This one, 3318 into 4,200. When I multiply by 2, that's 360 and 66. When you multiply by 4, it has to be double of this, right? 720, 132. 0, 6, 9, 3, 9, 13. 1393, 960. Into that 1.22 also I can make it up here. 1.22 divided by 2.5. 1.22 divided by 2.5. On the other side again you have 77 into 400, which is 30,800 plus 307.1 CL. Now what you have to do, let's add these two. That is 800 if you add there, 760, and then 9 is here, 3, 4, check that, 0, 6, 7, 4, 139. This is how we added, right? So that will be 142. Into 1.22 over 2.5, I can approximately assume it to be 2. Approximately. It's like 2.049 something. So we can take it as 2. 2 equals 30,800, 307.1 CL. Now see, like this much of solving we are getting because these numbers are the values we got from the experiment, right? What you get in the exam are values which are easy to solve. So don't worry about this. Like in the experiments, even if you take a calculator and solve it, doesn't matter much, because in the exam you don't get this kind of solving. Now again divide by 2. 712,380. 30,800, 307.1. Now subtract this 30,800 here. 30,800, 85, then 11, 1, 8, 681, 580 over 307.1 is going to be CL. Right? So it's more than 2,000. 2,000, shall we check? 681, 580, 307, let's say, 2, 614. Then you have 67, 5, again 2, 307, 614. That's 61. Again 2. Approximately 2,220 joule per kilogram per Kelvin. Joule per kilogram per Kelvin. Careful, the units are important. Units are important. Physics, every answer you give has to go with the units carefully. So the answer we are getting is approximately. Why I say approximately? We made a couple of approximation in solving this. Here 1.22 over 2.5, we took it as 2, right? So there is a small approximation. 307.1, I took it as 307. So approximately you can say 2200. 2200 might be a better approximation. You can take a calculator and check this correctly. And you know, coconut oil, we even the theoretical value, it's around 2100 is the theoretical value. So 2200 is very close to the answer that we study in the theory, right? So this is what we do to find the specific heat capacity of a liquid using the cooling method. What do? We let the water cool and draw the cooling curve. And whichever is unknown liquid, you draw the cooling curve for that also on the same graph. Then from one particular temperature to another particular temperature, find how much of time both have taken. Assume both are used at the same quantity, same type of surface. So all the cooling conditions were same. Therefore, you can equate the heat loss rate are equal for both the water and the oil with the calorimeters. Equate that, put all the parameters, calculate carefully. Bit of a lengthy calculation though, but if you have a calculator, we can solve it quickly. And don't worry, this kind of calculation for the exam, it doesn't come with numbers like this. In case if it comes, it will come with much easier numbers. So don't worry too much about solving it. Approximately, this is the answer we have got. Practice this again. Once again, you go through all this. Now what I'm going to do, take past paper questions from this and see how it has been tested in the exam. Shall we see that? Now, the past papers, the first one is from advanced level 1990 paper, 1990. The diagram shows the experimental arrangement to determine the specific heat capacity of a liquid by the method of mixtures. This liquid is filled in a calorimeter which is placed on cork pieces within a white beaker. State three factors that decide the rate of heat loss to the environment from the calorimeter and liquid. Right, from the calorimeter to the environment, the factors that decide the heat loss rate, you remember, surface area, nature of surface. We studied this during the experiment. Before the experiment, I explained this. Nature of surface and the excess temperature. Excess temperature. Next. State Newton's law of cooling and the conditions for it. What did Newton say? The cooling rate is proportionate to the excess temperature. Cooling rate is proportionate to the excess temperature. Right? When an object is let to cool, the cooling rate, we write that part, when an object is let to cool in the surroundings, the excess rate of its surrounding and the cooling rate are proportionate. The conditions, surrounding conditions must remain the same. Or constant airflow must be maintained. Next, water and the liquid are used in equal quantities in this experiment. Explain briefly as to why equal amount of water is used. Why it has to be equal amount? Then only the surface area will be same, so that the cooling conditions will be same. To have equal surface area, such that cooling conditions are same for water And for oil or liquid, cooling conditions have to be same. Right? For that, the area has to be same. Next, the diagram shows the cooling curves of water and the liquid. A is water, B is liquid. The heat capacity of calorimeter and stirrer is C, heat capacity. That means M into C altogether. What we usually write as M and C, mass and specific heat capacity. They multiply together and they are giving you the heat capacity. Mass of water is MW, liquid ML, specific heat capacity SW/SL. Write down the mean rate of heat loss from the calorimeter and the liquid when it cools down from θ1 to θ2. We have done this calculation. Yeah. How? C plus. Usually we write it as MCCC. MC is the calorimeter stirrer mass. CC is the calorimeter stirrer specific heat capacity. But here they have multiplied and they have given you heat capacity. Careful. And then ML SL θ1 minus θ2 over TL. It has taken TL time. You can see that here. TL. See this point to this point. It has taken TL. Write down the mean rate of heat loss from the calorimeter and water when it cools down from θ1 to θ2. This time it's water. So again, calorimeter, water's mass, water specific heat capacity, θ1 to θ2, and the time it has taken is from this point to this point, which is TW. Very easy, very easy. Next, write down the relationship between the expressions derived in 1 and 2. Both are equal. Since you use the same amount of water, same amount of the liquid, all the cooling conditions were same. Then you can say C plus M liquid, S liquid, θ1 minus θ2, T liquid equals C plus MW, SW, θ1 minus θ2, T water. Next, explain why a glass beaker cannot be used instead of the calorimeter in this experiment. The heat conduction rate will be less in glass. So what will happen? The water's temperature and the outer surface of glass will have different temperature. The internal water's temperature and the outer surface of glass's temperature will not be same. Because of this reason, we cannot use a glass. Right? We have to use a proper good heat conductor material. That's why we always say metal calorimeter. Metallic calorimeter made out of metal, usually copper or aluminium. You can say why it cannot be used. If glass is used, the temperature of water and outer surface of beaker will not be same. Will not be the same. Next. This is 1997 question. Another one, 1997. The diagram shows the experimental arrangement to determine the specific heat capacity of a liquid by method of mixtures. Same thing. Identify vessel A. It's a calorimeter. Vessel A is this one. Where do you keep this? If you have written beaker, glass beaker, then you don't get marks. You can either say metal vessel or metal container, or the correct name is calorimeter. What are the additional important instruments for this experiment? They have mentioned only about calorimeter here. important instruments, then you need a 3-beam or triple beam balance, stopwatch. Those are the main ones, right? Those are the main ones. Next. What are the factors that determine vessel's heat loss rate to the environment? Same question we had earlier also. Surface area, the nature of surface, then excess temperature, from the environment, Next, two separate cooling curves will be obtained for water and the liquid in this experiment. Compared to the quantity of water, how much of liquid should be used? Again, same question. It must be same amount, same quantity. State the reason for your answer in D1. Why do we use same quantity? So that surface area is maintained the same. To have same surface area such that cooling conditions are the same. Next, assuming that the specific heat capacity of water is greater than that of the liquid, draw rough sketch of the two cooling curves you can obtain from this experiment. See, let's say we start both from 80. Right, this is water. This is that's water. This is the other liquid, right? Since water has higher specific heat capacity, it cools slowly. The temperature drop will be slow there. Next, to find the specific heat capacity of the liquid, two quantities have to be derived from these curves. Show the construction to be done on the curves in E to obtain those quantities. We did that after the experiment. When we did the calculation, I showed you. You need to select two temperatures. Let's say from this point to this point. Then the time. Theta 1, theta 2. T, this is for liquid. This is for TW. Okay. Next. To find the specific, that's what we did now. Next. The heat capacity of calorimeter and stirrer is C. Mass of water and the liquid MW/ml. The specific heat capacity of water and the liquid are SW and SL respectively. Write down an expression that relates these quantities to the quantities obtained in F. Same question every time we write. They're asking us to write the equation C plus ML and SL. Theta 1 minus theta 2, I wrote that time as TL, equals C plus MW SW, theta 1 minus theta 2, TW, theta 1 minus theta 2, TW. Next, can this experiment be done by filling the space between A and the external beaker with water? Explain your answer. See, you have the beaker. Right, this is where the hot water is. What we usually do, we keep a fan and do this experiment. What if we keep it in another beaker? This is the calorimeter. We keep it in a beaker, fill this space with water. Look at this. Can we do like that? The problem is when this calorimeter releases heat, then the water is going to gain that heat. When the water gains the heat, temperature of this water is going to rise up, which means to this calorimeter, external conditions do not remain constant. Whereas throughout the cooling period, the external surrounding conditions have to be maintained constant. By filling this by water, it will be difficult for you to maintain it at constant level. We can do this, right? Keep it in like this. Look at this. Here what we do, this space is filled with cool water. Then what happens? The water quickly absorbs the water heat, and then time to time by changing the water we can do the experiment, right? So let's write that. No. The other arrangement I showed you when I was doing the experiment, I showed you, remember the other arrangement, if you want to maintain the surrounding conditions, how do you do it? Right, you keep the container within, you keep the calorimeter within a container. That is kept in another container. The gap between the two containers is filled with cool water. Whereas next to the calorimeter, it's the air only. And the cool water is time to time you keep replacing it. I have shown that in the experiment. If you want, go back and see at the end of experiment, I have shown that. So this is no. Explain your answer. No. The surrounding conditions cannot be maintained at same conditions. Surrounding cannot be maintained at same conditions. 2006, that's another past paper. See how easy the questions are once you understood everything. Once you understood each step as to why we are doing those steps, then answering the questions is so easy. Problem is you don't watch, you don't do the experiment, you don't watch somebody doing the experiment, you just memorize what is given in your notebook. That way you can't do it. You need to know the reason for each step. If they say, okay, let's fill the calorimeter with 1 centimeter below the top of it, ask the question why. Without knowing why, if you just memorize it, you can't do it. Right, so that's the important part. Now 2006, a student wants to determine the specific heat capacity of a liquid using the method of cooling. For this, he plans to obtain cooling curves for water and the liquid separately. All necessary equipment for the experiment has been provided. In this experiment, it is important to use equal volumes of water and liquid. Give the reason for this. In all three equations, they have asked it. What's the reason? To maintain the surface area equal. Surface area equal. Such that cooling conditions, the cooling conditions are the same. Such that the cooling conditions are the same. Next. Figure shows 3 different levels marked on the calorimeter. Of these 3 levels, up to which level the student should fill water or liquid to obtain a more accurate result in this experiment? You know, L1, right? From the top, just 1 centimeter below means L1. L2 and L3 are too low, not L2, L3. Give the reason for your answer. I explained, you remember, if you keep the water level low, then you can ensure the entire calorimeter's wall is maintained at the same temperature. Right? By doing this, we can ensure entire calorimeter wall is maintained at the same temperature. To maintain same temperature, on the full surface of calorimeter. Otherwise, what will happen? Listen, otherwise, what will happen? See, if you have taken like this and if you have put water only up to here, so this part will be at the same temperature of water. If water is 80, that also will be 80. Whereas the rest of the calorimeter, say this part, will not be at 80. That might be 60, 70, close to 80. Right? Then our cooling conditions and cooling rate, everything is going to be different. Might not, it will give you errors. Whereas if you fill it up to here, then we can say more or less all the calorimeter surface is going to be at the same temperature as of water. Next, what experimental steps should the student follow in order to make sure that the thermometer immersed in water or liquid reads the temperature of the calorimeter surface? Now look at this. We are talking about heat loss at this surface, right? Whereas you kept the thermometer here. So how do we know this temperature and this temperature are same? How do we know those two are same? Basically, that's why we keep stirring it. By keep on stirring it continuously, you can ensure throughout the water and water plus the surface of calorimeter all are maintained at the same temperature. If you don't stir it, that might not be the case. So how do we ensure it? By continuously stirring the water. By continuously stirring the water with a stirrer. We are given a stirrer, right? The two cooling curves obtained by the student are shown in the figure. Water and the liquid, time in minutes. Okay. What's the question on this? Other data: heat capacity of the calorimeter, mass of water, specific heat capacity of water, mass of liquid. What is the average rate of heat loss of the calorimeter with water during cooling from 55 to 45? Check 55 to 45. Let's draw a line there. 55, 45. So that's like 2 minutes, isn't it? 2 minutes. The other one takes 1 minute. No. Two gaps means this is 4 minutes. Water has taken 4 minutes. And the other liquid has taken, you can see here 55 to 45 here. That is 2 to 4, 2 minutes. 4 minutes and 2 minutes. First they are asking about water, I think. Water, yes. So let's write it. C plus MW into 4000 into temperature difference 55, 45 is 10. The time taken for that was 4 minutes. Let me multiply by 60 to convert to seconds, so that I can get joule per second. Otherwise, I have to say joule per minute. Careful. So this is 800, 912, 0 cancelled, 4 into 6, 6, 15 is 90, 12. Now if you divide this by 4, that is 3, 4, 3, 12, 32, 8. 38 joule per second, 38 joule per second. So you are losing heat at the rate of 38. Calculate the specific heat capacity of the liquid. Liquid's heat loss rate also has to be same. That is again C. C is 112. Liquid's weight is, mass is 0.172 kilogram into C liquid or S liquid, whatever, into temperature difference is 10. It took 2 minutes. That has to be same as of water. Water heat loss rate is 38. This also has to be 38. 10 cancel. So 112 plus 0.172 Cl is going to be 38 into 12. This 12 can be cancelled, I think. See, 12 if you divide, no, 12 cannot be cancelled. then we will multiply by 12 and write that. 12 into 8, 96, 9, 12 into 3, 36 plus 9, 45. So 0.172 Cl, if we subtract it there, it's 344, isn't it? 344. 624. Cl is going to be 344,172. Let's divide and see. If I divide by 8, 4, 3, 000. 8, 2, 1.5. So when you cancel it, that's 2000 joule kilogram minus 1 k minus 1, isn't it? 43 into 1000, 43 21.5 is twice. So 2 into 1000, which is 2000 joule per kilogram per Kelvin, right? This is what I told you. In the exam, if you get the same calculation, solving is very simple, not like the numbers we got in the experiment. Last part of this. Why is it not suitable to use glass container in place of the calorimeter in this experiment? Didn't we have this question in 1990 paper, the previous paper? Same. What are you going to say? The glass surface temperature will not be the same as the water's temperature. The temperature of water, temperature of glass surface are not going to be same, right? So what you read as the temperature of water in the thermometer, whereas the heat loss happens from the surface, which is going to be different. Clear? Right. So that's all in this experiment, using cooling law, finding the specific heat capacity of a liquid. That's all we have. I clearly explained you the theory. I did the experiment. Each step I explained you why we are doing that. Most importantly, learn that. Why? Why do we take this step? Why do we take this measure? And then I have shown how this is tested in the exam also. Practice all this, understand everything. Let's meet up with another experiment soon.